Hello YouTube, welcome back. Today I'll be working through some practice problems for polynomial functions. So these practice problems will be basically covering what's been covered so far. So that includes leading coefficients, degree, end behavior, just those, not multiplicity yet. That'll be the next video and the next practice work. So yeah, let's get straight into it. So number one, identify whether or not each function is a polynomial function. Okay, so we're given this function over here, and I'm noticing this part seems fine. It's okay. I mean, we've got our terms, we've got our coefficients, we've got our nice whole number exponents, but what I'm looking at over here is we have a variable exponent, and for polynomial functions, having a variable exponent, that doesn't classify as a polynomial function. So we can say this is not a polynomial function because it has a variable exponents. And there we go. So basically for polynomial functions, you can't have a variable function, otherwise it's not classified as a polynomial function. So let's move on to part B. And it asks us, we're given the function x. We're given the function 7x squared plus 3x minus 4 all over this right here. So what I immediately see is I can immediately rule out this is not a polynomial function. And the reason for that is basically we're dividing the numerator by the variables on the bottom. Like we're dividing by 8x cubed minus 2x squared plus 1. What this looks like is if we have 7x squared all over 8x cubed minus 2x squared plus 1, and then we're also going to have 3x and then divided by the same thing over there. What I'm noticing is we're going to end up with an exponent that is not a whole number. And in order for a function to be a polynomial function, you must have an exponent that is a whole number. And this is probably going to result in either a negative or a fractional exponent. So I can immediately rule that off. So let's quickly write that in. So let's say not a polynomial function because it would result in either fractional or negative exponents on the variable. There we go. All right, let's move on to part C. So we're given the function p of x equals 7 times x to the negative 5, and so on. So what I'm noticing here is this part onward seems pretty normal. It's pretty standard for your polynomial function. You have nice whole number exponents, and nothing's fishy going on. But when I look at over here, things start to become a bit strange, because what I'm noticing here is you have a negative 5 as an exponent. And what we know is we can't have negative exponents. So we can immediately say not a polynomial function because there is a negative exponents on a variable. There we go. Okay, let's keep going. Let's move on to part D. So we're given p of x is equal to 17 plus 2x squared minus 8x to the 6. This seems pretty normal. I mean, we have our nice whole number exponents. They're not negative. They're nice whole numbers. We have good coefficients. They're real numbers. And yeah, I'm not seeing anything weird. So we can actually say that this is, in fact, is a polynomial function. So there we go. So when determining whether or not a function is a polynomial, what you want to look at is first look at these exponents. A polynomial function can only have whole number exponents, basically 1, 2, 3, 4, 5, 6, or 0. It can't be negative, or it can't be fractional or decimal. And also what you want to look at is if if you can't have a variable as an exponent. So right here, we notice this exponent was a variable. A polynomial function cannot have a variable as exponents. And yeah, this also ties into the first point I mentioned. If you're dividing by something, make sure your exponents they don't become fractional or negative. Otherwise, that would not be possible. So let's keep going on. Let's move on to question number 2. So it says for each function, identify the degree, leading coefficient, and end behavior. All right, so let's start by degree. So we can say degree. So what I'm noticing here is what we have to do is look at the highest exponent on the variable. So this is an exponent of 2, this is an exponent of 1, and this is an exponent of 3. So the highest exponent on the variable is 3, so we can say it's a degree of 3 because 3 is the highest exponent. And for the leading coefficient, it's just whatever is next to the highest exponent. So that's just gonna be a 2. So you can say leading coefficient is 2. And now we have to identify the end behavior. So now that we know these two key pieces of information, this is what's going to help us to determine the end behavior. So since it's a degree 3 polynomial, that means it's a odd exponent. That means basically we're going to have an end behavior going like this. So spanning out from quadrant 3 to quadrant 1. If you're unfamiliar with this end behavior stuff, I recommend checking out the video I made about the introduction to polynomial functions. We talked about how the end behavior for odd degree and even degree polynomials are, as well as for negative or positive leading coefficients. So there we go. Since this is a odd degree polynomial and there is no negative attached to it, we're just going to be going from quadrant 3 to quadrant 1, so we can write that in. So we can say from end behavior is from quadrant 3 to quadrant 1. Perfect. All right, let's keep going. Let's go to part B. So we're given p of x equal to minus 4 times x to the 5 and so on. So first, let's figure out the degree. So what is the highest exponent I see here? Well, the highest exponent on the variable I see is 6 because 5 is less than 6 and also 1 is less than 6. So we can say it's a degree 6 polynomial. And what else do we have to solve? We have to solve for the leading coefficients. The leading coefficient is whatever is next to the highest highest exponent. So we can just say 3. So you can say leading coefficients is 3. And it's a positive 3 because there's a positive attached right there, so we don't have to include anything. And for the end behavior, let's figure that out. So notice for even degree polynomials, our end behavior looks something like this. We're going to be going from quadrant 2 to quadrant 1. Yeah, that's for even polynomials. Because there's no negative attached here, that we're not going to be flipping. We're not going to be going down there. So we're just going to be sticking to the first 2 quadrants, so quadrant 2 to quadrant 1. So you can write that in. So we're going from end behavior from quadrant 2 to quadrant 1. There we go. Let's move on to question C. So we're getting the polynomial minus 7 times x4, all of this stuff. And let's figure out the degree first. So we can write in degree. And I highly suggest for everyone who's watching this to give this question a try. If you're comfortable with what we've been doing, what I've discussed, then I recommend giving these problems a try and pausing the video and working through some of these problems. So I'll give you a sec for that. Hopefully you have given it a shot. So I'll begin solving it now. So what I'm noticing here is the highest degree is 4 because the highest exponent on the variable is 4 because nothing is higher than 4. So you can say degree of 4. And for the leading coefficients, it's whatever's next to the highest exponent on the variable. So that's going to be a negative 7 right there. So you can say leading coefficient is negative 7. Make sure to include that negative there. It's important. And for the end behavior, let me just write an end behavior. Okay, so let's analyze this. So it looks like we have an even degree function. So normally for even degree functions, we have an end behavior going from quadrant 2 to quadrant 1, quadrant 2 to quadrant 1. But since there is a negative here, what's going to happen is we're actually going to go for quadrant 3 to quadrant 4. Everything gets flipped. Because of this negative right here, we're going to be flipping our end behavior, and we're actually going to be going from quadrant 3 to quadrant 4. So you can say end behavior is quadrant 3 to quadrant 4. Yeah, this negative flips our end behavior. So let's keep going. Lastly, for question D, it asks, we're given this polynomial, minus 2 times x to the 9, and so on. So let's first identify the degree. So we have degree, and I'm noticing the highest exponent on the variable is 9 right here. And so we can say degree of 9. And we can also figure out the leading coefficient, which is just going to be -2, because that's what's attached to it. So you can say leading coefficient is -2. And let's just write an end behavior. End behavior. Okay, so let's analyze this, what's going on here. So now that we know what's going on with this, the degree leading coefficient, we can easily solve for the end behavior. So let's draw in our Cartesian plane. And normally for odd degree polynomials, our end behavior spans out from quadrant 3 all the way up to quadrant 1. But since this leading coefficient is negative, we're actually going to be going from, let me choose a little bit lighter. We're actually going to be going from quadrant 2 to quadrant 4. Quadrant 4, this is quadrant 2. Because what's essentially happening here is this is going up to here because we're flipping it, and this is going down to here. So our end behavior will be from quadrant 2 to quadrant 4. So we can write that in. Quadrant 2 to quadrant 4. So instead of being from quadrant 3 to quadrant 1, with our typical odd degree polynomial, we're going to be going from quadrant 2 to quadrant 4, since our leading coefficient is negative. And perfect. Let's move on. So lastly, question number 3, it asks us, match the equation with the correct graph. Okay. So we're given 4 different graphs here, and we have to match the equation. So what I'm going to do straight off the bat is figure out my end behavior, because that's going to tell me exactly which one of these graphs my equation matches up with. So in order to figure out the end behavior, I'm going to need degree. So we can write in degree. So it looks like my degree is going to be 3, because that's the highest exponent on the x variable. So we can say degree is 3. And for leading coefficients is going to be -3 right there. -3. Okay, perfect. So now that we've got our 2 key pieces of information to determine our end behavior, let's figure it out. So let's draw in our coordinate map here. And normally, for odd degree polynomials, our end behavior, again, goes from quadrant 3 to quadrant 1. But since it's negative, everything gets flipped. So instead, we're going to be going from quadrant 2 to quadrant 4, because everything is being flipped. This is going up to here, and this is going down to there. So we're going to be from quadrant 3 to quadrant 4. So we can actually just write that in just to be safe. End behavior quadrant 2 to quadrant 4. All right, so let's see which one of these graphs goes from quadrant 2 to quadrant 4. So this one, it looks like it's going from quadrant 2, but it's going to quadrant 1. So this means A can't be the answer. Let's look at B. Looks like B is going from quadrant 3 to quadrant 1. That can't be the answer. And C is just going from quadrant 3 to let me just draw these arrows to be helpful. It's going from quadrant 3 to quadrant 4, so therefore even C can't be answered. That means we're left with D. And it looks like we're going from quadrant 2 to down to quadrant 4. And would you look at that? This matches up. So that means our answer must be D. Okay, there we go. That is how to answer these types of problems. I'll see you in the next polynomial lesson.